These last couple of examples that we did actually leads us into a nice little theorem, and it's based on the family of curves of the form 1 over x to the p. And the theorem says the integral from 1 to infinity of 1 over x to the p dx is equal to 1 over p minus 1 if p is greater than 1, and it's divergent otherwise. And that's what we saw here, because this first integral we did was 1 to infinity of 1 over x dx. Here p equals 1, and this integral, it went to infinity and it was divergent, which is what the theorem says. The next integral we did was from 1 to infinity of 1 over x squared dx, and here p is equal to 2. According to theorem, this integral should actually be equal to 1 over 2 minus 1, which is 1, which is exactly what we found. So for these two examples, this theorem worked perfectly. So let's go ahead and actually prove this theorem. Now I'm going to start off by just integrating the thing using the techniques that we've already done. So I'll take a look at the limit as b goes to infinity of the integral from 1 to b of x to the negative p dx. Simply rewrote this. This equals the limit as b goes to infinity of x to the negative p plus 1 over negative p plus 1 from 1 to b. I'm going to rewrite this as the limit as b goes to infinity of x to the 1 minus p over 1 minus p, evaluated from 1 to b. That wasn't a necessary step, but I think it cleans it up a little bit. And I think the last thing I'm going to do before I start doing anything real serious with it is I'm going to take this 1 over 1 minus p and pull it out. So this is the same as 1 over 1 minus p times the limit as b goes to infinity of x to the 1 minus p, evaluated from 1 to b. Now I'm ready to actually do something with it. But what I'm going to do is I'm going to break this up into 3 different cases. Case number 1, I'm going to let p be greater than 1. That is actually this scenario right here. So if this theorem's correct, when I integrate this, and when I evaluate this under the condition that p is greater than 1, I should get this result. So note that if p is greater than 1, then 1 minus p is going to be less than 0. If p is bigger than 1, I take 1, subtract something bigger from 1, I get a negative number. Well, that means that the exponent is going to be negative. So I can rewrite this as 1 over 1 minus p times the limit as b goes to infinity of 1 over x raised to the absolute value of 1 minus p. And I'm going to evaluate this from 1 to b. So that's going to be 1 over 1 minus p times the limit as b goes to infinity of 1 over b raised to the absolute value of 1 minus p minus at x equals 1 of 1 over 1 raised to the absolute value of 1 minus p. Well, this is just going to be 1. So this piece right here is going to go to 0. This would be a negative 1 because of that negative right there. So the solution will be a negative 1 over 1 minus p, which if I factor out this negative, so it cancels out with that one, I'll get 1 over p minus 1, which is exactly what the theorem said I should have. So now let's take a look at the next 2 cases. The next one I'm going to look at specifically p equals 1. Then the third case will be when p is strictly less than 1. So case number 2, p is equal to 1. Well, if p equals to 1, then the integral that I actually have is the integral from 1 to infinity of 1 over x dx. We already did that. That is infinite, therefore divergent. We did that in a previous example. So we know what that answer is, and that's exactly what the theorem said should happen. So what about case number 3? I'm going to let p be strictly less than 1. See, now I have 1 over 1 minus p times the limit as b goes to infinity of x to the 1 minus p. But notice, if p is less than 1, this then indicates that 1 minus p will in fact be positive. It's always going to be greater than 0. That means I have a positive exponent here. So I can evaluate this as 1 over 1 minus p times the limit as b goes to infinity of b raised to the 1 minus p, and keep in mind this exponent will always be positive, minus 1 raised to the 1 minus p. Well, this is going to go to infinity, so this is going to blow up. Therefore, it's divergent. And that's exactly what the theorem said should happen. So we just proved that that theorem is, in fact, correct.